So we can combine gas laws even farther. We've already seen how Boyle's law and Charles' law can be put into what's called the combined gas law. We throw Avogadro's law in there also. We get what we call the ideal gas law. So the ideal gas law is this right here. PV equals nRT. Some students remember that by calling it PIV-NERT. PV equals nRT. So in the ideal gas law, there are 5 terms. We're familiar with pressure, volume, and moles of gas and temperature, and then there's this other one, R. R is a constant. All the other things we've looked at were involving changes or proportionalities, and so there were proportional constants in there, but they're not useful, so we didn't talk about them. The reason that this does not have 1s and 2s and multiple letters and big complications is because we've got this proportionality constant in here. A constant is constant, it's always the same. And so this is the value of the constant, 0.0821, and the units look weird, right? But it's liters times atmospheres divided by moles times Kelvin. When you use the ideal gas law, you have to use these units. So the pressure needs to be in atmospheres because that's in the gas constant. The volume has to be in liters because that's the unit in the gas constant. The amount of gas needs to be expressed in moles because that's in here. And the temperature, as always, has to be in kelvins. So the ideal gas law allows us to calculate one property, pressure, volume, amount, or temperature at a fixed situation if we know the other things. So we don't have to look at changing. There's also another law called Gay-Lussac's law that relates pressure and temperature. These are all the simple gas laws, and all of these can be derived from the ideal gas law. So I'll just take a minute to show you how to do that. No? There we go. So starting with the ideal gas law, PV equals nRT. So that's not too hard to memorize. If you have a situation where volume's changing or pressure's changing or something's changing and you need any of the other laws, you can make them out of this. So take one ideal gas law and divide it by itself. PV equals nRT divided by PV equals nRT. And then put subscripts. Put 1s on the top and 2s on the bottom. Now, is the gas constant going to change? R. No, that's not going to change. R divided by itself is 1, so that goes away. Ooh, that was too big. So the R goes away. Now, you can take this and look at your problem and see what's changing. If it's changing, it stays. If it doesn't change, it goes away. So let's say we had amount of gas changing and we had temperature changing. But the pressure was constant and the volume was constant. Well, if the volume is constant, that means that volume 1 is equal to volume 2, right? They probably wouldn't even tell you what the volume is in the problem, but it's not changing, so it doesn't matter. So that would mean that the volumes go away. And the pressure is also constant. The first pressure is equal to the second pressure. So anything divided by itself is 1. So those go away. So what are we left with over here? 1, because they canceled out. 1 over 1, if it makes you happier. So here is the relationship. It's in a different form, but it is the same relationship. I'm having a brain fart. I picked those badly because we don't have anything in here. So, good grief. Okay. Rewind. Oh, come on. So let's try that again. I wanted to end up with something recognizable, but I didn't think it through. So let's say the volume and temperature are changing. Volume and temperature are changing, because we've done that one. Yeah, we've done that one. And that means that pressure and amount of gas are the same. So the pressures cancel out, the moles of gas cancel out, because they're not changing. So I get that V1 over V2 equals T1 over T2. That is the same as V1 over T1 equals V2 over T2. So I think that's easier than memorizing equations. Okay, where am I? So let's use the ideal gas law. So here's the question. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. If you notice that nothing's changing, you can go directly to using the ideal gas law. If you are word problem challenged and you just like go, wah, when you look at this, follow the same pattern. We're going to make a table. Okay. So we'll just set this up like we did all the other problems, 1 and 2. We're going to put the numbers in as we go across. So 0.845 moles. And we're going to call that column N because N stands for number of moles. And then we've got 1.37 atmospheres. And that's the pressure. And we have a temperature of 315 Kelvin. And like it must be Christmas or something. They gave us the temperature in Kelvin, so we don't have to convert that. We ran out of numbers. There's only one row. Oh, we didn't need to make the table. Did we waste our time? No, we've got everything all labeled. So let's get rid of the rest of the table. Didn't need it, it's okay. No harm done. So nothing's changing. This is ideal gas law problem. PV equals nRT. What are we trying to find? The volume. Calculate the volume. So we take this equation and we rearrange. So I'm going to divide by P on both sides. So the P's cancel out. So the volume equals the number of moles times the ideal gas constant times the temperature divided by the pressure. We need to know what R is. I will give you R. 0.0821. And the units are liters times atmospheres divided by moles times Kelvin. These are the units that you have to have on all of your other quantities. So I'm going to put in moles. N equals 0.845 moles. And next up is the ideal gas constant, 0.0821 liters times atmospheres divided by moles times Kelvin. And then I'm going to multiply that by T, 315 Kelvin, and divide that whole mess by pressure, 1.37 atmospheres. Check the units before you do the math. Kelvins cancel kelvins, moles cancel moles, atmospheres cancels atmospheres. If your units don't work out, then you may need to convert your pressure or your temperature or something into the correct units. Always check the units. 0.845 times 0.0821 times 315 divided by 1.37 equals. The volume is 15.951. The unit is liters. 3 sig figs on all the things I was given, and so that's going to round to what? Yeah, question?
Last semester, our check gas was C0.08206. Would you rather us use the rounded version?
This is, I was debating whether to say anything about that. I don't know why they round this. It's 0.08206. It can actually be calculated out to even more digits than that. I would prefer that you use 0.08206. That's better. It's more precise. The book uses 0.0821, and so as to not confuse people, I'm trying to go with that. But good question. So when we round this, the 5 rounds the 9 up to a 10, and so we get 16.0 liters. Any questions? Yeah. Well, these are the units on the constant. And so I'm not going to put, you mean putting numbers in here? Yeah. It's confusing because this is this huge mess of a unit. But it has these units so that they are going to cancel out with everything else in the ideal gas law. We don't often see messy units like this because we give them a new name. Like a Pascal is a Newton per meter squared. Instead of writing Newton per meter squared all the time, we just call it a Pascal. So we could have a different name for this, but it's actually helpful to have these units there because then we know which units we're supposed to use. Let's do another one. An 8.5 liter tire is filled with 0.55 moles of gas at a temperature of 306 Kelvin. What is the pressure of the gas in the tire? Do you want to do the table or do you want to do the other way? Table? So, we've got a gas problem. We're going to make a table. We've got 8.5 liters. And that's a volume because liter is a unit of volume. 0.55 moles. That is the symbol N. N for number of moles. And a temperature of 306 Kelvin. Again, they're being kind to us and giving us the temperature in Kelvin. You still have to use Kelvin here. You can't use Celsius. So we started the table. We don't actually need all of it. It's okay. What is the pressure? So ideal gas law, PV equals nRT. This time we're solving for pressure, so we're going to divide both sides by volume. The pressure equals nRT divided by V. So N, 0.55 moles. R, 0.0821 liters times atmospheres per mole Kelvin. Temperature, 306 Kelvin. That's a crappy 6. 306 Kelvin. Divided by the volume this time, 8.5 liters. Write all the units in here. Write these units as a vertical fraction, not as a slash fraction on one line. Make sure that the units are going to work out. So I have Kelvin and Kelvin, I have moles and moles, I have liters and liters. Cross them out. .55 times 0.0821 times 306 divided by 8.5. 1.625 should have 2 sig figs, and the only unit that isn't crossed off is atmospheres, so that's my pressure, 1.6 atmospheres. Any questions? Yeah.
Do we need to memorize the 0.08?
No, I'll give that to you. Yeah, it's a good question. Any other questions? How much volume does 0.556 moles of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees Celsius? So, I don't know what I'm doing. 0.556 moles so that's going to be N, and 715, actually, I'm going to start over. So I'm going to do it the other way with just labeling things. So 0.556 moles. So that's N. N is number of moles. The next number that comes along is 715 millimeters of mercury. That's a pressure. And the last number is 58 degrees Celsius. That's the temperature. This will still work if you do it in the table. I just have limited space on the slide.
Do you have to convert that to liters?
We have to convert millimeters of mercury to atmospheres, and we have to convert degrees Celsius to kelvins. So this is an ideal gas problem, and it's going to use the ideal gas constant, 0.0821 liters times atmospheres divided by moles times Kelvin. I'm going to give that to you on the exam. There's a lot of help hiding in there. That tells us what units we need for these things. Millimeters of mercury are not going to work using the ideal gas law. They're fine in Boyle's law or Charles' law. It's fine. Temperature, always, 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 always in kelvins. Always. So let's convert that to kelvins. 58 plus 273. 331. So we got that taken care of. Moles of gas, that's fine, but we do need to change this one to atmospheres, the pressure. So the relationship between millimeters of mercury and atmospheres, 1 atmosphere is equal to 760 millimeters of mercury. You will save yourself a lot of time if you memorize that, but I will give it to you. So 715 times 1 divided by 760. So 0.940. There's my 3 significant figures. Put down 2 extras. Atmospheres. Don't round things before the final ending answer. Make a note of sig figs, but don't round it all off. I wrote really big. So we're looking for volume. PV equals nRT. We're solving for volume, so we divide by P on both sides. And volume equals nRT over P. So number of moles, 0.556 moles. Oh, this is not going to go well, is it? I'm gonna move down here. Volume equals the number of moles, 0.556 moles, times the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin, times the temperature in Kelvin, 331, divided by the pressure in atmospheres, 0.94078 atmospheres. Moles cancel, atmospheres cancel, kelvins cancel. I'm left with liters. Do the math, 0.556 times 0.0821 times 331, divided by 0.94078. And my calculator shows me 16.0604, 3 sig figs. And the unit is liters. So this is going to round to 16.1 liters of gas. Any questions? We can use the ideal gas along with a measurement of mass to calculate the molar mass of a gas. Finding molar masses is often not really very straightforward. You can use a very expensive instrument called a mass spectrometer, or you can do some somewhat sophisticated reactions where you look at combining ratios and things to figure out what the molar mass is. With gases, you can actually calculate the number of moles if you measure the volume, the pressure, and the temperature of the gas, and then you can weigh it to find the mass. And so then molar mass is the grams divided by the moles. So in this example, a sample of gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. So this is a problem that you should know how to do. Well, we've been doing ideal gas problems, and this is different, isn't it? Well, what is molar mass? Do I have this on another slide? Is that the same? No, that's a different one. I'm going to do this one because it's got more space. And I don't think I need to do 2 of these. These are very similar problems. So here we have a gas sample with a mass of 827 milligrams. Here's its volume. Here's its temperature. Here's its pressure. Find the molar mass. So you ask yourself, well, what is the molar mass? What's molar mass mean? We sometimes abbreviate it capital M, molar mass. That is the mass of it in grams divided by the number of moles. Usually it's 1 mole weighs this many grams, right? But you could do it on a smaller scale as long as you know the mass and you know the number of moles. So what we need is the mass of this sample, and we need to know how many moles of this gas do we have. We can use the ideal gas law to calculate the number of moles. So PV equals nRT. This time we're trying to find N. So we're going to divide by RT on both sides. So N equals the pressure times the volume divided by the ideal gas constant times the temperature. Well, what's the pressure? 976 millimeters of mercury. Is that going to be a good unit? No, because ideal gas law has atmospheres in it. So we need to convert that. So we've got our pressure. Pressure is equal to 976 millimeters of mercury. So to convert that, I multiply by 1 atmosphere and divide by 760 millimeters of mercury. I put that in there so the units work out. 976 divided by 760. 1.2842 atmospheres. So that goes in here. 1.2842 atmospheres. So I had to convert the pressure. The volume. Here's the volume. The volume is this. It's given in liters. Is that a good unit? Yeah. So I don't have to mess with that. 0.270 liters. And then I'm dividing by the ideal gas constant, 0.821 liters atmospheres per mole Kelvin. And then I need the temperature in there also, 88 degrees Celsius. Is that going to work? $88 No, thank you. Thought I lost you there for a while. 88 degrees Celsius. We need to convert that to Kelvin. 88 plus 273. 361 Kelvin. So that also goes down here. I've got atmospheres canceling atmospheres, liters canceling liters, kelvins canceling kelvins. I end up with a unit that is 1 over moles, which is moles. I can show you how that works if you want me to later. So 1.2842 times 0.27 divided by 0.0821. I don't know what happened to my 1 down there. I've got 0.82 L. Yeah, that's better. 0.821 divided by 361. And my calculator gives me 0.011. I'm looking at sig figs. I should have 3. 116. Write down 2 extras, 98. Units moles. Everybody okay with that? So that's the number of moles. So molar mass is the mass in grams divided by the number of moles. Well, I just found the number of moles. 0.011698 moles. How much does that number of moles weigh? 827 milligrams. Well, I want my mass to be in grams per mole, so I'm going to have to convert that. 827 milligrams. So I want grams on the top and milligrams on the bottom. So the units are going to work out. Dimensional analysis, over and over and over again. Milli means 10 to the minus 3. I have milli in the denominator. I don't have anything representing milli in the numerator, so I'm going to put what milli means up there, 10 to the minus 3. So that ends up being 0.827 grams. So I have 0.827 divided by 0.011698 equals. I'll put this in a different color because otherwise it's going to be completely lost in my mess. Three sig figs, so would be right there. So my final answer, there's nowhere to put that, 70.7 grams per mole. Sorry, that's such a mess. Is that a reasonable molar mass? Yeah. What if it was 0.7 grams per mole? Would that be reasonable? Would it even be possible? What's the smallest element? Hydrogen. What's the mass of hydrogen, molar mass? It's 1.008 if it's by itself, just atoms, but it's usually as a molecule, so it's 2.016 grams per mole. I can't have a molar mass that's smaller than hydrogen. That means I did the calculation wrong. Okay? Could it be 100? Could it be 500? Sure. It could even be 1,000,000. There are some really big molecules called DNA. But if it's less than 2, something went wrong. Any questions? So we've been talking about the ideal gas law. What do we mean by an ideal gas? Well, a gas that behaves like we think it should. Sort of the ideal child who doesn't exist, right? Well, gas behavior is sometimes ideal and other times not, and it depends on the conditions. So we think about kinetic molecular theory, and everything works out very well when we have high temperature and low pressure. So under these conditions, the gas particles are moving fairly rapidly, and there's lots of empty space. So the size of the particles compared to the amount of empty space, the size of the particles is really, really small. It doesn't really matter very much. And the interactions between these particles are insignificant. Because when two gas particles run into each other, they're coming in so fast that they don't have time to interact. It's like brushing through people in the hallway when you're racing to catch an airplane or something. You know, you don't look to see if they're cute or they smell good or anything. You're not attracted to them. You just keep going because you're on a mission, right? So here the gas molecules are moving quickly. They're on a mission. They're not interacting. Non-ideal conditions, we've got low temperature and high pressure. At low temperature, the gas particles are moving more slowly. They're strolling along. When they bump into each other, they have time to chat and they may interact with each other. And so that affects the behavior of the gas. Also, there's a lot less empty space, and so now the size of the actual particles are becoming important. I thought there was more. There isn't any more. So when a gas gets very crowded, or when the particles are moving very, very slowly, the ideal gas law doesn't work very well. So I want you to know that that exists, that happens, but we're not going to worry about it, okay?